Hello and welcome back to Alakazam Math Made Easy. In this video, we're going to go over essentially the connection between the concept of limits, which we just finished, and the concepts of derivatives, which we're just starting, right? So naturally, there has to be some logical connection between one or the other, and we'll explain that in this video. But what I really wanted to start with is what the concept of a derivative is. So a couple concepts here are combined, right? So first, if you recall the definition of a tangent line, right? It's that I can look at the slope at any of the points that I want, and I can draw a line that bumps right up against that curve at that point, at that x value, and I can find the slope of that tangent line, which should essentially translate to the slope of the function at that point, right? But if I were to draw, for example, the point right here next to this green line, that slope is going to change, right? From the green dotted line to that blue point next to it. And I could even draw a line in between those 2 points and it'll be different there. So essentially what's happening is that no matter how close you get to the x value you're at, the slope of that tangent line is going to change for a complex function like f of x here. So a derivative is essentially a function that we can use and then plug in the x value we want to return the slope of that function at that point, right? So the derivative itself is a function, and then we plug in, and the derivative function describes the original function. It describes the slope of the original function, actually. And then we can plug in the x value that we care about. So say I wanted to find the derivative at this point here, x equals 2. I can plug in 2 into my derivative function and it'll populate, like plug it into my calculator, it'll populate the slope of that original function at x equals 2. So one more thing I wanted to jump into before we jump into the actual connection between limits and derivatives is the actual formatting that we use to indicate a function versus its derivative. So we're going to operate with the same assumption that the function will be called f of x, but remember it could also be called y. It could be called, for example, g of l. It could be any 2 combination of letters, but what we're going to end up seeing is that the indicator that we're talking about the derivative of that function is that there's going to be an apostrophe now. So for example, y would become y prime and g would become g prime of l, right? So instead of f of x, it could be g of l, it could be p of n, it could be whatever. But the derivative will always have that apostrophe, which we call prime. So that apostrophe, if we're saying it out loud, this becomes y prime or f prime of x. So that prime piece is how we indicate verbally that there's an apostrophe there. So now that we've got the actual, for example, formatting out of the way, we can look at the connection between limits and derivatives, and that is essentially what we're going to call the mathematical definition of a derivative. And that's saying that I can approximate the derivative function by taking the limit as this h value goes to 0 of x plus h, f of x plus h minus f of x over f of h. So that's just a function that we can use to plug and chug. And we'll go through an example real quick. And then I believe there's an example to work through together. Yes, awesome. So for this example, we're finding the derivative of f of x equals x3 using the definition of a derivative. So one important thing to note is that it says just find the derivative, not find the derivative at x equals whatever. So if it says find the derivative without telling you where you're looking for the derivative, it's actually asking for the function, not the slope value. So for example, the first step is going to be to plug your f of x that you are given into the equation for the definition of a derivative, right? So basically, all I did here was I said, all right, if the function is f of x equals x cubed, I can plug that in right there. And f of x plus h, remember, if you're doing this, all you do is you plug in whatever is inside those parentheses in for everywhere you see x. So that's why this piece here says x plus h, the quantity cubed. So there's that. So now we've plugged it in, now we can start evaluating. The first step we're going to need to do is we're going to need to break up this piece here into a polynomial, right? So that's why we do this. So remember, x plus h cubed is equal to x plus h times x plus h times x plus h. So what I did in this step here is I FOILed it once and I multiplied it by itself again. So I basically combined these two into x squared plus 2xh plus h squared. And then still we have to multiply it by another x plus h. So that's how I got to this step down here. So what I'm going to do is I'm going to erase these markings so I can explain the process a little better. So now we've expanded it to what we have here in this bottom line. So now it's time to simplify it, right? So we're going to simplify first by canceling this h, right? We don't want that h there anymore because that makes it a fraction, which is unnecessarily ugly right now. So we're going to cancel an h with every term that has an h. Oh, wait. Just kidding. No, that's the next step. So first, before we do that, it's probably smartest to consolidate all of your terms, right? So here, for example, we have an x cubed and a negative x cubed. So those are going to cancel. And then also we have a plus 2xh and a plus 2xh. Oh, wait, wrong one. Hold on. We have a plus 2x squared h and an x squared h here. So that's going to be this 3x squared h at the bottom. And then, so that's going to go here. And then we have an xh squared and a 2xh squared. So that's going to go here. And just add them together. And then finally, you have an h cubed, which is just going to go here. And remember, these x cubed values cancel each other. So now what we're going to do is we're going to go in and cancel this h to get rid of that fraction, right? So I'm going to cancel this h. I'm going to cancel one of these h squareds. I'm going to cancel one of these h cubes, which leaves it as an h squared. Okay, so now we have it in our simplest form, right? Now we have it down to this function down here. And what we're going to do then is, now that it's simplified and easy to evaluate, we're going to plug in that h is 0. So for everywhere you see an h, we're going to plug in a 0. So here we'll plug in a 0 and we'll plug in a 0. So that becomes this term canceling, right? Because 3 times x times 0 is 0. And this term canceling because 0 times 0 is 0. So all we're going to end up with is this function here, f prime of x equals 3x squared. And that's our derivative. So I wanted to work through an example together so you can kind of see the logic of how it goes, right? So first what we're going to do is we're going to say f of x is 2x squared plus 3x plus 1, and f of x plus h is 2 times x plus h squared plus 3 times x plus h plus 1. And another thing you can do is you can simplify it before you plug it in, so it's a little bit easier. And that's what I'll do here. So I remember this is going to be x squared plus 2xh plus h squared plus 3x plus h plus 1. So we have a 2x squared plus 4xh plus 2h squared plus 3x plus 3h plus 1. And it doesn't look like any of those can cancel as they're written. So now it's time to plug in both of these values into our equation, right? So we have f of x plus h, so 2x squared plus 4xh plus 2h squared plus 3x plus 3h plus 1. And we have to do minus f of x, which means we're doing minus this whole function here. So what we're going to do is we're going to distribute a negative sign into all of these terms and just subtract them like that. So it's going to be minus 2x squared minus 3x minus 1. And all of that is going to be over h. So our next step is we have to cancel the things that are being subtracted, right? So here's the easiest way to do that. That's the first subtracted term, negative. And then this one cancels this one, and this cancels this. So that's what we have so far. Now let's see if we can combine any of these terms. Looks like not. So then what we're left with is the limit as h approaches 0 of 4xh plus 2h squared plus 3h over h. And what we're going to do, like we did before, is we're going to cancel this h with this one of the squareds, and this one. And that will leave us with the limit as h approaches 0 of 4x plus 2h plus 3. And now that it's in its simplest form, we're going to evaluate that limit. So we're going to end up with f prime of x equals, and we're plugging in a 0 for everywhere we see an h. So this term is going to cancel. So it leaves us just with 4x plus 3. So a lot of times people get a little bit flustered because of this formula can lead to structures that are pretty big. Like this is a big equation the way it's written, but it usually simplifies down to something relatively nice looking, right? So there's that. Another common question that people have is, if I'm going to just be plugging in h anyway, why don't I plug in h at this step, right? And if you remember, one of the issues with that is that, for example, look at all of these terms cancel anyway, right? So all of those would end up going to 0, right? But if I plug in h here, I get 0. If I plug in h here, I get 0. And if I plug in h here, I get 0. So I have 0 plus 0 plus 0 over 0. So remember from the limit section, if we end up with the limit equals 0 over 0, limit as h approaches whatever, equals 0 over 0, that's not useful to us. So that's why we have to simplify it as far as we can into its simplest form before we plug in the limit, because only then will we get something that doesn't equal 0 over 0. So that is essentially the connection between limits and derivatives, but also it is formally known as the definition of a derivative. So if you learned something from this video, please like it. If you want to keep up to date with the videos that I upload to my channel, subscribe and press the bell button to get notifications when new videos are added. And as always, best of luck.